Hello, everyone. I hope you're healthy and well. Thank you for joining us for the next talk in our Golden Webinars in Astrophysics series. As you perhaps know, we have arranged for simultaneous language interpretation provided by Mr. Patricio Gonzalez, Director of Serendipia Soluciones, who will be simultaneously translating for us again in both English Spanish to English directions. To avoid some of the confusion that one or several of our viewers have expressed with the language channels, Ricardo will give now a brief explanation in Spanish as to how to change the language for this talk in your Zoom windows.
Bienvenidas y bienvenidos todos. Les cuento, en sus dispositivos pueden escuchar la interpretación al español de la conferencia al pinchar el botón de interpretación que se encuentra en la parte inferior derecha de la ventana del Zoom. Ahí deben seleccionar español. Esto además les va a permitir cambiar la pista de audio de la conferencia entre ambos idiomas. Desafortunadamente, la opción de interpretación en vivo no está disponible para las personas que usan el Zoom en el navegador o en computadores con Linux. Les pedimos disculpas por esto y pronto publicaremos las versiones en inglés y en español de la charla en el canal de YouTube del Instituto de Astrofísica de la Pontificia Universidad Católica. También sabemos que algunos participantes han tenido algunas dificultades para silenciar la pista de sonido original al escuchar la traducción al español. Esto se debe a un error en Zoom y la solución es que ustedes puedan salir y volver a entrar al seminario para poder solucionar este problema.
Excelente. Muchas gracias, Ricardo. Bueno, welcome again. So my name is Thomas Puzia. As you probably know, I'm a faculty member at the Institute of Astrophysics of Pontificia Universidad Católica and the head of outreach activities at the Institute. And together with my colleague, Evelyn Johnston, who you also probably know, who is one of our postdoctoral fellows at the Institute, we are and will be organizing this series of talks for you for as long as we can. Thank you so much for all your feedback, your comments and suggestions. We really appreciate your encouragement and support. If you would like to support this series, please send us an email. The address can be found on your webinar registration notification or on our YouTube channel, Astrofísica. If you like these talks, please share them also with your friends and colleagues. It supports our channel. We will continue to bring you these talks in the original English and Spanish, simultaneous Spanish translation, as we explained, which has been made possible by the generous support of the Center for Astrophysics and Related Technologies, also known as CATA for its Spanish acronym. Our talk this evening will be given by Michael Nolan, who is the OSIRIS-REx Science Team Chief. First, though, we will give you a very brief introduction into how the webinar will run.
If you have any questions during the talk, please type them into the Q&A window. All viewers will be able to upvote questions and comment on them, and we have a team of astronomers and journalists working behind the scenes to monitor the questions, and we'll select the best questions for the discussion at the end of the talk. The talk is expected to last around 45 minutes, and we'll have time for questions at the end, and the questions will only be taken from the Q&A window. Unfortunately, we can't monitor the questions coming up on the YouTube channel at the same time. Before we begin, I'd like to briefly introduce our panel members today. As usual, we have Thomas Patricio and we have Mike, our speaker. From the Institute of Astronomy at PUC, we have our postdocs Giuseppe Dago and Paul Eigenthaler. And it's our pleasure to welcome our guest panelists this evening, who are Susan Ridgway and Jayadev Rajagopal, who are scientists at the NSF National Optical Infrared Astronomy Research Laboratory. And we have Angela and Maren Hempel, who are astronomers at the University of Andrés Bello here in Santiago. And finally, we have our usual excellent team of Q&A managers, Ricardo Acevedo, Daniela Fernandez, and Carol Rojas.
So it is our pleasure to introduce Mike Nolan as our speaker this evening. Mike's career started with his undergraduate degree in chemistry at the California Institute of Technology in 1985. Followed by a PhD in planetary science at the University of Arizona, which he completed in 1994. He then had several research associate positions at the University of Arizona and then the National Astronomy and Ionosphere Center at the Cornell University. He then became the Deputy Director of Planetary Sciences at Arecibo Observatory in 2011. And in 2015, he was appointed Senior Research Scientist at the Lunar and Planetary Laboratory at the University of Arizona, a position that he still holds.
As part of his current position, he has been a key member of the OSIRIS-REx spacecraft mission, with roles including the mission geophysical scientist and the mission science team chief. OSIRIS-REx is an asteroid sample return mission, which aims to collect samples from the Bennu asteroid and will bring them to Earth for analysis, with the aim of answering some of the open fundamental questions, such as where did we come from? But Mike can explain all of this much better than we can. So let's hand over to Mike, who will tell us about 20 years of Bennu from Arecibo into orbit and back again.
All right, can you see my presentation?
That's great.
Okay, thanks. Of course, it went into presenter mode, so I can't see anything else. Okay, as was said, I'm going to talk about the OSIRIS-REx mission. It's a sample return mission to the asteroid Bennu. This is a pretty accurate cartoon of the spacecraft. It has a lot of instrumentation, but of course the primary instrument is this sampling arm here, and this is showing it on its way in to take the sample of the asteroid Bennu, which it will then pack away in this container and bring it home. And so now I've been involved in this mission in a sense longer than it's been a mission. And I'll be talking about that as we move along. All right, most of the imagery I'm going to show you is publicly available if you want to go look for it. This asteroidmission.org is our team website, and there's a whole lot of imagery there, and almost everything that I'll show you is going to be there. We have the usual other social media contacts. So just in brief, as you heard, so the point of the OSIRIS-REx mission is to fly to the asteroid Bennu, characterize its surface, and return at least 60 grams of pristine material from the surface. And I'll be talking about the things we've learned along the way there. So here is a closer look at the spacecraft. It has as usual, it has an antenna, solar panels, and it has a fair amount of instrumentation. There's this Rexus instrument is an X-ray imaging experiment. It's a student project, so that was done by some students at MIT and Harvard, and they built this instrument and flew it, and have been taking X-ray images of the surface of Bennu and of space in general. There's a whole bunch of cameras because as we go all different distances from Bennu, we need cameras with different properties. So there's what we call SAMCAM, the sampling camera. And that's what we'll be imaging when we actually go and collect our sample. Its main feature is that it has 3 cover glasses, so that if the system is designed so that basically we get 3 tries to actually go grab the sample. And so if we get the lens dirty on one of them, it can rotate to a new clean lens for the next try. There's the MapCam, which as its name implies, is the mapping camera. It's what we think of as our medium resolution camera. It has a filter wheel so that it can take color imagery of the surface, global color imagery, and that's been a really neat product. That it's 4 colors basically going from blue to near infrared. There's the Polycam, which is a telescope. It's poly. Because we use it for several different things, but it's got a variable focus, and it's the highest resolution camera. So it's the one that's taking the sub-centimeter resolution imagery, and it's the highest resolution, and it can go anywhere from because it has a focuser. It can go anywhere from finding Bennu when we were infinity as a telescope, up through taking this extremely high resolution imagery from about 100 meters altitude. We also have some spectrometers. There's OTES, is the O is for OSIRIS, is the thermal emission spectrometer. And so it's a spectrometer that goes from something like 6 to 100 microns wavelength. And that's been, we were expecting to do a lot of our site selection based on the thermal properties of the surface, and that has proved quite valuable. There's the OSIRIS, which is another infrared spectrometer. Visible infrared. It goes from 0.4 microns to 4.3 microns, so it covers the visible spectra, near infrared, out past the water and carbonate and organic bands. There's also OLA, which is a laser altimeter, and it's a mapping altimeter, and so it scans a laser, and that has proved to be one of the primary instruments that we've been using for examining the shape of Bennu, which, as you'll see, has been more important than we actually expected it to be. This big white thing in the middle is the sample return capsule. And so when all is said and done, the sample will come into here, and this is actually mounted on a spring, so that when we fly home to Earth, this just gets pushed off with a spring, and it will re-enter the Earth's atmosphere as the rest of the spacecraft flies by. And the sampling arm is full. You can't see it really very well here. It's full. It's this object here, and it's folded up behind the spacecraft. And I'm going to get rid of this because it's kind of in the way. So I have my countdown timer here that says we're going to be tagging the surface Bennu. We call it tag, touch, and go. We don't really land. We reach down and grab our sample, and that'll be in 1608 hours, 34 minutes, and 13 seconds. It won't let me close that. Oh, there we go. Okay, so this is a sample return mission, and that has had some interesting effects on the way we operate. So our primary objective is to bring back a sample. We have a lot of scientific instruments, but we're mostly using them to figure out, to do our site selection, where should we bring back the sample, and to help us figure out how to deal with the surface of Bennu, which of course we had never seen up close until we got there. So this cartoon sort of shows you how the sampler works. This is the sampler, and it's we're showing it having sampled a bed of sand. Partially, when we first were going, we were kind of hoping we would find a place with something like sand. And basically, it's a vacuum cleaner that you push the head of the, you push this sample head down onto the surface, and then blow. There's a tank of nitrogen, and you blow nitrogen into the surface, which throws material up into this sample container. And these holes here are to let the gas out, so that the solid material gets trapped inside this head. Under optimal conditions, you can collect up to 2 kilograms of sample. Again, our goal is 60 grams, and of course, we're hoping for more than that. But that's the design. We're going to, so the asteroid that we're going to, Bennu, is of what we think is what we call a primitive asteroid. It's got a lot of organic materials, and it's relatively unprocessed. And if we're trying to look at organic materials on in our return sample, we had to spend a lot of effort checking, anytime you build something, you're going to contaminate it. People are involved. There's going to be bits of organics and oils and things just from the people assembling it. They do the best they can, but nothing is ever perfect. And so one of the main things we did was document exactly what it is that was on the spacecraft, so that when we get the sample back, we can understand what's really from the asteroid and what is not. So our goals are 60 grams of sample. And the other thing that it has is you can't see here, but on the face of the sampler, there's a bunch of actually Velcro pads, the stainless steel Velcro pads, and it turns out that dust and sand-sized particles get stuck in those very easily, and that even if for some reason we went and touched down on something that didn't let us get a much solid sample, we would get little grains attached to the front. All right, so when we went to Bennu, we had to choose where to go. And we chose Bennu based on several criteria. One, it comes fairly close to the Earth. It's relatively easy to get to. You can see the orbit's over here. Bennu's orbit crosses the Earth's orbit, and in fact, it comes quite close to the Earth every 6 years. So in 1999, and that's where the 20 years comes from. We were able to get radar observations, and so we were able to get crude images of the surface of the shape of Bennu, from which we made a shape model. So in numerical modeling, we used numerical modeling to make a shape model. And so what did we know about Bennu when we went there? And we knew about how big it was. It was a little under 500 meters in diameter. It's basically round with this sort of 2 cones stuck together shape. Rotates in 4.3 hours, which actually turns out that information was quite important, because that way we know if we're going to go take images of a complete rotation, we knew how many images that would be. So that helped us size our data storage and data transmission. It's got an obliquity of just about 180 degrees, meaning that it's essentially almost perfectly retrograde, and there's which we think is probably related to the round shape and some solar radiation effects that tend to do that. The bulk density, we knew from actually studying its orbit very carefully. The bulk density we knew was about 1260 kilograms per cubic meter, and we knew that by looking at, again, solar radiation forces on the orbit. We had a lot of radar data. We had 3 epochs of radar data, and so we were able to measure its orbit very precisely, and from that actually get an estimate of the bulk density. We knew the albedo was about 4.5% because we know how big it was and we know how much light it refracts. That's approximately the albedo of charcoal. And in fact, you probably don't know if you can see it, but we made some plastic models. And I remember when I first made them, in fact, it's gotten kind of shiny. When I first made them, it's hard to see the surface with your eyes because it's so dark. And that's actually kind of true, that it has a that dark surface makes it interesting to study. And, the spectral type is B. Like a lot of things, when we have this asteroid taxonomy, and B's and C's and G's are dark, presumed to be organic rich materials, and its spectrum matches pretty well that of the carbonaceous chondrite meteorite, which are the most primitive kinds of meteorites. And so we thought this was a very good candidate for having primitive material left over, relatively unprocessed since the formation of the solar system. Certainly we thought it was unmelted. It might have some aqueous processing, and it certainly has been in the inner solar system, and so it's been warmed, but it's never been melted. All right, so when we got to Bennu, of course, it doesn't. It's not that sort of round, smooth blob that you saw in the ship model I was showing you before was 20-meter resolution, and here's the Bennu we actually got to, and so this is of course much higher resolution than we had before, and you can see some of the same features. So like that rock right there, we were able to see this one coming around here. We were able to see in the radar imagery, but basically most of the other features we couldn't see. One or two of the rocks, knowing they're there now, I can go find them in the old model, but they were not obviously visible. You can see that this surface looks pretty rough. It's got a lot of rocks on it. And so we didn't get that beach that we were kind of hoping for, and has been seen on some other asteroid. The asteroid Itokawa that the Japanese Hayabusa mission went to had some very smooth areas, and we were hoping for that. Now this set of images was taken at fairly high phase angle, and that does sort of emphasize the rough surface, but nonetheless, so this surface is noticeably rougher than we were planning for. As I said, I started off on this project at Arecibo. In fact, I specifically proposed to do this observation as a fairly new person at Arecibo, with the idea that some of the asteroids we would be looking at might eventually be spacecraft targets. And in fact, on my job application to Arecibo, that's one of the things I put down, is that we were going to be we wanted to study these asteroids because they were potential spacecraft mission candidates, and we needed to study them. I will take a short aside right now. Some of you may have heard that there was a problem at the Arecibo Observatory earlier this week. And so as you can see, this is the Arecibo Observatory. This is the spherical reflector dish. And all of the business, all of the optics, all the electronics and that stuff are up in this dome. This dome is suspended from these 3 towers by cables. And each of these things that looks like this one cable, there's actually 6 cables in there. And what happened was one of these cables came loose. It came out of its socket up here at the tower end. Now those cables are under a very high tension. They're about 3.5 meters, so maybe 10 centimeters in diameter, galvanized steel cable. And so under a lot of tension. And so when that came undone, the cable snapped, and it made an impressive looking hole in the dish. It did some damage to the dome, and clearly it's also just to some extent the damage that it did to those structures, I don't expect to be sort of fatal. Those are things that can probably be fixed with a lot of work, but they're not fatal. The real question is, why did it come out, and is there any other danger to the structure? And of course, that was one of the cables holding it up. So now the other ones are having to do more work, and there's some concern about the stability of the structure. They have an engineering team working full time figure out one, how to make it immediately safe, and then they'll start working on repair plans. So it's sad when problems like this happen. They've had a very rough couple of years. I guess we kind of, this is just another one of those 2020 things, I guess. But they went through a hurricane a few years ago, and we're just starting to be really recovering from that when they got this new problem. All right. So anyway, this is where we took the radar images. The way Arecibo works is it's a spherical reflector, and then the azimuth and elevation drives are up on this triangle. This dome moves in and out to adjust the elevation, and then it rotates around to the azimuth. So it turns out you can observe asteroids for about 2 hours at a time. And so in 1999, and again in 2005, we did those observations. So these are, on the left, you see what radar images look like. This is an image that we did took in 1999. It's an image sequence that was, excuse me, this is 15-meter pixel spacing. The web version of this video makes it look a little worse than it really is, but it's still a pretty low resolution image. But from that, we were able to make this shape model, which is the one we used for planning the mission. Let me see if I can get that to play again. No. So this is how I came into the picture and how we were able to do a lot of the planning we did, because we knew a lot about the asteroid to start with. And so we had, again, we had before we got there, we had some predictions about the surface. One is we did know there was one kind of big boulder. You can see that little dot right there. That's the boulder. We had said it's bigger than 10 meters. Well, it turns out it's closer to 40. Again, these are 15-meter pixels, and so it's always hard to figure out what sizes are at that scale. So, so these two images are, this is from 1999, this is from 2005, so that we know it's a real feature because it repeats. And these are the models we made from these images. Radar images are kind of funny because you measure distance and you measure velocity from Doppler shift. And so, right, you measure round trip light time for the signal to get there and back, and you measure the Doppler shift of the signal. And so you can think of it as if you were looking down from the North Pole, and the illumination is from the side, and that's what these images are. Those are hard to sort of visualize as a human, but of course we can program the computer to figure out what the shape would have to be to make those images. And so we kind of thought they were small we thought the particle sizes were pretty small, and that we had one big boulder. When we got there, so here's our initial approach imagery from late 2018, and rotating in sequence with the original shape model. You can see that the boulder, that the shape is grossly right. You can see the one boulder in our model is this boulder here. You can see these sort of flat spots that are in the model. To some extent, when you're looking at a model like this, you're never really sure how much of it's noise and how much of it's real. I'm pleasantly surprised at how good it was. That really every feature in here appears to be a real feature. There's almost no noise in the model. You can see that the real object is perhaps slightly less pointy than the model, but people have always asked us, how well does this radar modeling work? And the answer from this picture looks to be that it's pretty good. And we were particularly concerned, there's an ambiguity in radar data that makes it difficult to measure the length of the z-axis, because it turns out to be ambiguous, and nonetheless we got that just about right. So we're very happy with that. Of course, since then, we've now made a new shape model using the imagery. And again, this is just sort of to show you that we can do a lot better now, of course, but that again, qualitatively, we were happy that the radar imagery worked, and we were able to get a good prediction. Of course, now that we've been there for a year and a half, we have based on the LiDAR, we have really good shape models, and your quiz, your very short quiz is to figure out, so one of these is the shape model and one of these is imagery. And at first glance, it's not all that easy to tell which is which. And so that means we've done a really good job modeling. Now, it isn't actually all that hard to tell which one, because this is a laser ranger model. So it doesn't have any kind of color, any brightness variation. So you can see in the real images that there are some bright rocks and some dark rocks, and that's not something that shows up in the model because it can't see that. But that we have an exquisitely precise and accurate model of the asteroid. So we have the model we have has 5 centimeter ground sample distance. The precision of the model is about 2 centimeters. The absolute accuracy is approximately 10 centimeters. And this is one of those just, every time I really think about it, it's pretty amazing. Nobody's ever made a model like this of a deep space object. And so it took a huge amount of work to do this. And it also turned out to be very important. When we originally designed the system, we didn't expect to have to target nearly as precisely as it's pretty clear that we're going to need to do. All right, so once again, here's Bennu. There were a couple of surprising things that we saw when we got to Bennu. One is this very rocky surface. Another one is what happened when we started looking for satellites. Now, there are binary asteroids that have moons around them, and so one of the first things we did when we got to Bennu was we took extremely deep images of Bennu, of the space around Bennu. So we've overlaid an actual image of Bennu on top of this very highly stretched deep space image. The horizontal stripes are some camera artifacts that are residual. And we didn't see any satellites, we didn't see any particles. We didn't really expect to, because they should have been visible. Anything big should have been visible in those radar images. We didn't have it, but nonetheless, we wanted to be sure. So we didn't see anything. Well, about 2 months after we got there, we were taking some navigation images, and we saw these weird things. This is also mosaic. This a short exposure of Bennu combined with a long exposure on the sky, and you can see this swarm of particles near Bennu. This was pretty scary. That we hadn't expected that we would have this shooting off these particles. We had a lot of concern about whether they would be a problem. We eventually concluded that they were probably too small. They're typically 1 centimeter or 2, and they're moving 1 meter a second or less, and so they're not actually dangerous, but they were pretty exciting. And we were able to actually compute orbits for some of them. So here's the orbit. Here's Bennu. Here's the spacecraft orbit around Bennu, and then here's the orbits of the particles. So some of them are actually in places where they could crash into the spacecraft. We never, I think in orbit, we've never seen any evidence that we've been hit by a particle, but space is big, and but that was pretty cool. Yeah, they were discovered in navigation images. In fact, they were actually discovered when one of the scientists was looking to see if we could get one of those Earth-Moon portrait images where the spacecraft is imaging the Earth and the Moon, and he saw a lot more than he was expecting. Mostly pea-sized. The largest, is about 10 centimeters. We have a few, actually this slide is out of date. We have way more than 200 objects with fits. That's as of almost a year ago. We've kind of reduced the rate at which we're searching for these now based on data rates, but we are still seeing particles coming off. And there's here's this the biggest particle ejection event. You can see that as Bennu was spinning, we computed the orbits of each of the particles based on looking at how they were changing in the imagery. And you can see some of them get just spit off, some of them go up and come right back down, and a small fraction, probably a couple of %, stay in orbit for days to weeks. And that's, I don't know, it's pretty cool. The other thing is just how rocky Bennu is. We had, so based on ground-based thermal inertia measurements, we had estimated that the particle sizes should be a few millimeters, typical particle sizes. And from the radar, we couldn't tell the particle size, but we could tell that they were probably either smaller than 5 centimeters or bigger than 10. So the reflectivity, we used 2 different radars. One had 10 centimeter wavelength, 12 centimeter wavelength, and one had 3.5. And the reflectivities were the same at both of those wavelengths. And so we said, well, either the particles aren't about that size. They're either smaller than the smallest wavelength or larger than the largest wavelength. Based on the thermal data, we said, okay, so they're probably smaller than the smallest wavelength, so they're probably a couple of centimeters. Well, that turned out not to be true. That, in fact, the particles are clearly, the typical particles, there's a lot of meteor rocks. One really cool thing that we don't really understand is that some of these big some of the biggest rocks have thermal inertias that are not consistent with any rock on the Earth or the Moon. And so we presume it means that they're porous in order to get the very low thermal inertias that we see. But it's very hard to really prove it. We measured thermal inertia by using the thermal spectrometer at different times of day. We went and looked at Bennu and took global thermal measurements from lots of different points of view, and so that we could see what it does over the course of a day and a night. And basically it cools down and heats up faster than makes sense for such for what appears to be a competent rock. And so that was a very big surprise. And it did also mean that the surface is a lot rockier than we were expecting. Again, here's some, of course, these big rocks. And one of my big question of those is, okay, something made this sort of round shape. A lot of the ways we think this happens has to do with it spinning up and down, although it's possible that it's basically just a collisional artifact. But somehow these pretty big boulders ended up just sitting on the surface. And that's, I suppose, not hard to explain in a sense, but it's just not a very intuitive behavior. Of course, anytime we're dealing with something like an asteroid, the physical conditions are really different than it is possible for us to sort of really imagine as Earth-based beings. That imagining such low gravity is hard, but basically we always make approximations like, oh, it's in the strength regime where strength is important, or it's in the gravity regime where gravity is important. Well, now we have a surface that has very low strength. It's a rubble pile, and it also has almost no gravity. So it's extremely difficult for us to figure out which of those things is the most important. We see some very cool what we think of as sort of brecciated rocks. This rock looks like it's made up of a bunch of chunks. It's got some sort of brighter things and some darker things. And so this rock has been processed in some way that it's gotten sort of smunched together, but yet, like the other ones, it seems to have a very low density, so it's a confusing thing. And then we have another one that kind of looks like one of those rocks that fell into pieces. And so this, I think our current notion right now is that thermal processing probably makes these things shrink and then expand over day and night, and maybe that breaks them into pieces. So there's features like this several places on the surface where it looks like, we call them campfires informally, where it looks like one big rock just sort of fell to pieces. And it also looks like there's different kinds of rocks in there. You can get fooled by lighting. If the lighting is from this side, then that will look brighter, and that can fool you. We do try to correct for that the best we can, but nonetheless, that's just an odd thing. Another one where it looks like a rock that has little bits in it. So something has processed this material and sort of broken it and recombined it into a single piece. We see some evidence that the surface has moved. This looks a lot like this crater-like thing that we actually call this region Boulder Town. Again, informally, looks like there's on the edge of a surface, and that the rocks have been sort of falling down into it. So something here is collapsing somehow. This may have something to do with right now the asteroid is spinning up from what's called the Yorp effect, which is a thermal effect. And so the period is increasing by about the period is decreasing by about 1 second per century. So over time, it's spinning up, and that might make things move. But it looks like things are breaking and moving around. We see one very big crater. We have a few what looked like to be pretty big craters. This is about 130 meters. Depending on the nature of the surface, the age of this crater should be something like a few 100 million to 1 billion years old, which is much older than Bennu can have been as a near-Earth asteroid. Bennu is a near-Earth asteroid. Near-Earth asteroids can stay in that sort of place, sort of 10 million to 100 million years before they're dynamically ejected, usually ejected from the solar system. They're delivered from the asteroid belt on comparable timescales. So this crater almost certainly comes from when it was in the asteroid belt. Again, the surface of Bennu is very confusing. It has some things that make it look young. This shape, we think, may have a lot to do with its spin state, which would suggest that it might be young, but yet it has very old craters on it. And it has a lot of small craters that, smaller craters that are almost certainly younger. We see, so we have some, there's a 10-meter crater. Here is a very pretty 20-meter crater. This is actually one of the potential tag sites. It's actually currently our backup site. And so clearly there are craters. That means that can give you a lower limit on the age of this of the surface. Again, it's older than I might have guessed based on just our original models before we got there. And we do have some places, fortunately, where we do see this fine-grained material of the kind that we're looking for to bring home. Right? We can't really bring home a 1-meter boulder. It'd be nice if we could, but the spacecraft is not able to do that. We need to grab smaller bits, a couple of centimeters, and we do see some places with a couple centimeter particles. This was our favorite one, but this big rock here is 9 meters tall, and the spacecraft is about that big. And so we were pretty sure that we weren't going to be able to get into this crater without being too worried about hitting that rock. One thing that another kind of place where we see small particles is that we have some rocks that look like they've had other rocks just fall down on them. And maybe this has something to do with these particle ejection events, but like in this particular example, it looks very localized. So again, we don't really know literally what this is, but it does look like some material has fallen down onto the surface. You can see not just that rock, but you can see a lot of little brighter particles here that look like they may have fallen down onto the surface. These are bigger than we would have expected. But these are bigger than the ones that we mostly see from the particle ejection events. But of course, we've only been looking at those for a year or two, and the surface has been doing whatever it's doing for much longer than that. Just another view of that so that you can see little particles appear to have fallen down onto the bigger rocks. And some more of those where you have particles that look like they've fallen on top of other particles. Now, you always have when you say, oh, gee, it looks like a rock on top of another rock. Well, the whole thing is a pile of rocks. So something does have to be on top. But these really do sort of look like somehow in the formation you ended up with the rock sitting there and others sort of drifting onto the top of them. We have rocks that appear to be cracking. A few places where you'll see a big crack in a rock, right? This is a couple meters across. We also see some places where it looks like there's a rock that has had a piece of it fall down to the side. We presume that these are probably some sort of thermal cycling event, and this might have something to do with the particles, but that's one of these interesting processes that we're studying. And this is something that actually makes us pretty optimistic about the sampling, even if we do hit a rock, is that these rocks appear to be fairly crumbling. It looks like they're kind of falling apart. And so we're kind of thinking that if we hit one, we might actually smash it and bring home the smashed pieces, and that would be fine. All right, so we have all those spectrometers. What did we learn? So we have 4-color imagery, which has the advantage of being relatively high resolution. So but it only has those 4 colors, so it's difficult to attribute to do too detailed of analysis of what you're seeing. But you can look for differences around the surface, and you can look for the places that have interesting things. Then we have the point spectrometers that go from, again, 0.4, they actually go out to about 4.3 microns. This red spectrum here is the ground-based spectrum that we went in with. The things we're most interested in are the water band. This is the water band. So it's very difficult to observe water from the Earth, although it's not impossible. But so this is a clear presence of either this spectrum can be caused by water, which can either be water trapped in clay minerals, but it's more likely to be something like serpentine, where water has actually reacted with the rock. And what you're seeing is that this is an OH stretch. And so you're seeing hydroxyl on the surface. And so that's an indication of aqueous processing. And then out a little farther, this little dip, I don't know why, I guess this little piece here is either organics or possibly carbonates. Those are very difficult to tell apart based on in this spectral region. Then we have the mid-IR spectrometer that goes right from 6 to, it actually tweaks out to 100 microns, but 50 is the most we usually do. And you can see small features here, which are at least consistent with magnetite, which is an aqueously processed mineral. And so we think there's been some aqueous processing going on here. And that makes some sense. A lot of primitive meteorites do have clays in them and do have aqueously processed materials. And so we're seeing, and that one of the things we're looking for in the sample site is to find some of this primitive looking material that has been processed in interesting ways. And again, so the black spectrum here, these are again the mid-IR, and so you can tell that this black spectrum here has features in common with a lot of different kinds of meteorites. So we're happy that it does look like we're getting what might be one of the sources of primitive meteorites. One of our real hopes, just sort of from a fun point of view, is we said those rocks look very crumbly. It's very plausible that all these rocks that we're seeing on Bennu would not survive if they get dropped into the atmosphere. They would be just turned to dust and crumbly. And so it's possible that there are no meteorites from asteroids like Bennu, that we may be going to an asteroid for which we do not have meteorites to match. One of our understanding of the composition of the solar system mostly comes from meteorites. and we tie those meteorites back to asteroids and back to the formation mechanisms. But it's quite possible that a lot of the asteroids that we think these things came from, it's possible that meteorites from those asteroids don't survive, and that maybe there are other things that are really more representative of the bulk of the asteroidal material, and that would be a really cool discovery. I don't know what that's about. Ah. All right, yeah, so the positions of these bands are the ones that people look at to try to correlate the compositions. All right, so we took, again, global spectra, global imagery, in order to choose a sample site. This was a sample return mission. All of that science is done in furtherance of choosing the sample site. So we chose 4 potential sites. One's we give them birth. So Bennu is a mythological bird. It was chosen based on the Egyptian theme of the name of the mission in a contest, and so all of the features on Bennu are named after birds or bird-like creatures, mythological. So our names for these are informal names for the sample sites are also birds. So the 2 main features sources now are this nightingale and osprey. It looks like I need to speed up a little bit. So here are images of each of those sites. Nightingale has the best looking material. It has this scary rock right over here. We informally call it Mount Doom. It's 8 meters tall. We need to get in past it without anything bad happening. Here's the Kingfisher site. This actually has really good material, but we just decided it was too small. We couldn't be sure we'd get there. Here's the Osprey site. It's the biggest, safest site, but the material's not as interesting as Osprey. And then Sandpiper turned out to be rougher than we were hoping for. So the orange circle around here was the design for how well we had to be able to hit the sample site. And as you can see, we need to go a lot closer than that. So this is a cartoon of the parking lot behind our building, and pretty clearly we have to fit into one of those parking spaces to go get our sample instead of this big circle. We actually had to change the way we do the navigation significantly in order to meet that. Turned out the spacecraft is quite capable of doing it, but we had an an autonomous navigation system that wasn't in the original design in order to do that. There's Osprey again. That was Nightingale. This is Osprey. It has this big rock, but that's far enough away that we can avoid it. We're not right now. The big question: if this is our backup site, if for some reason the first one doesn't work, right now our question is: are we going to go here, which is sort of a very safe area, or maybe over here that looks a little darker but is closer to some other rocks? That's still a decision that we're working on. There's one of our not quite highest, but one of the highest resolution images of the Nightingale site. You can see it still has rocks, but it has a lot of places that just don't look like they have much in there, meaning that the material that's there is smaller than we've resolved, and so that it's small enough that the sample site can probably pick it up. Here's a very high resolution images of Nightingale. This whole thing is 4 meters across. This is just a random place. I just grabbed an image, but these little rocks here that you can see all through there, those are sampleable. Our sample mechanism can pick those up. And again, if we hit one of these, maybe we'll slide off and get a piece. Maybe we'll push it in and get some, or maybe we'll actually just crumble it. We currently think we have approximately a 60% chance of hitting a real dirt patch that we know will fill the sampler. We have a few percent chance of getting close enough to something that's scary that we would have a problem. And if we do that, we'll back off. The system is smart enough to say if it thinks it's gonna hit a rock, it'll back away. So here is we call checkpoint rehearsal. The way the system works is this is the sample arm. We're heading in. This is a rehearsal we did a couple of months ago, and you can see we're getting close to the site, and then we back away. Checkpoint is the place where we readjust the trajectory in order to get where we want to go. And just last Tuesday, see if this works. Just last Tuesday, we did what we call match point rehearsal, which is where we get close enough that we actually match the orbit. So we just got this image on Tuesday. It downloaded yesterday. And so this is brand new. You can see that we're practicing. So we have the sampler arm out. We would have hit right there, I think, after the fact. We said, yeah, we probably should have just gone, but we didn't know that it was going to do quite that well that time. And so we're getting there. So we have a couple more months to go before we actually sample. And you can see that, again, the tag site's right about there. And we're getting closer and closer to it. This experiment ended at about 40 meters altitude. All right, so this is the final frame from that last video, the actual tag site. I've circled there. We're headed in. You can see that the arm is tilted a little bit, so the camera isn't pointing literally right at the arm is pointed right at the tag site, but the camera is offset a little bit, so it's not, that's why it's not quite in the center of the field of view. So on October 20th, right, we're gonna go and nitrogen gas will blow into the surface. That'll stir up the material, knock it into the sampler. Then we're going to go hold the sampler up into the sun, and you can see that the sunlight shines through the mesh. So hopefully we'll be seeing a whole lot of rocks in there. And then we'll put this in the sample return capsule, and then we'll head home. When we get home, we'll arrive home September 24th, 2023. I don't remember the exact time of day. It's known to the minute, just because orbital mechanics works that way. We do, when we do this, we're very much hoping to see that it's full of rocks. If for some reason it doesn't work, we do have 2 more tries. That have to be done before approximately next April, so we have to start thinking about heading home. Of course, there are other missions to asteroids. We knew kind of what Bennu looked like, but the Hayabusa 2 mission to Ryugu is about twice as big as Bennu, but it's remarkably similar looking, which was not known in advance. Ryugu actually was one of the targets that the OSIRIS-REx mission had looked at originally as a target, but we chose Bennu because we knew more about it. It's even rockier in a way, but it's got a lot of bigger rocks, and we were surprised that it was so similar. So to some extent, we're always discovering new things about asteroids just because they're just at the edge of what we can actually do. So here's the calendar. We arrived at the asteroid at the end of 2018. We spent about a year going and studying it in great detail. Now we're doing these rehearsals where we're getting ready to go sample. Our first sample collection attempt will be October 20th it's 2 p.m. Mountain Standard Time. And then we have a couple more opportunities if we need to, and then we'll be heading home about 6 months after that. Again, there's lots of ways to see pictures. Like at the beginning, everybody was very nervous about letting things out. Now we have so much. We're just putting as much as possible out onto the web and on social media, just because it's so cool. And that's all I have. I'll have to get out of here so I can understand any questions that come up.
Thank you very much, Mike. That was very interesting. Do we have any questions from the panel before we go on to the audience questions? Okay, so Angela has some questions. Angela?
Yeah, they are kind of related, so maybe I put them all together. You mentioned that Bennu could have been formed or could have been like 1 billion years old, while the surface is constantly like recycled by weathering effects and whatever. Do you have an idea when Bennu actually left its place of origin in the asteroid belt?
So we think it actually left. Well, we think it really got to the near Earth space probably something like 10 million years ago, give or take a factor of 4. it probably had a collision in the asteroid belt that in the asteroid belt that sort of put it into its current form, and that probably happened longer ago than that. And that's probably the event that we're seeing when we look at the older stuff on Bennu. Is we think that's probably a few 100 million years ago that it got put into that shape. It wouldn't survive for billions of years. It's too small, but that sort of couple 100 million years is probably when it got made into a thing. And then, so the asteroids are delivered by resonances mostly with Jupiter and Saturn. And so there's the solar radiation forces that kind of push the orbit around a little bit. If it gets into one of the resonances, it comes to Earth very quickly, a few million year time scale. So we think it's been here a few million years, but it's been this thing for probably 100 to 300 million years.
Yeah, and maybe it's related. Since these weathering effects, what temperature range is actually does the surface experience during its rotation when it goes from the sun away?
Yeah, so the cold temperatures are probably as cold as about 200 Kelvin. The high temperatures vary from probably 330 to maybe 370 Kelvin, depending on where it is in the orbit. If it's the close part of the orbit, it can be 370, 380 even, so pretty hot. So it's not a pristine sample in the sense of it's been kept cold, but yeah, a couple of 100 degrees is the temperature throw over the course of a day.
Okay, thanks.
Nice. Before we go on, can I ask you, Michael, to stop sharing your screen so the audience can see the people who are asking the questions? I think we're going to go to Maren next. She had some questions.
Yes. First of all, this was so interesting. Thanks a lot. And I wanted to ask, as you said, some of the larger rocks which show there is some substructure, will the instruments have enough spatial resolution to check whether this is just a mechanical compound of the same material or whether this is real chemical difference in these regions?
The remote sensing instruments on the spacecraft don't really. The IR spectrometer, the near IR spectrometer has a spot size. We got it down to a few meters at the closest time it was usable. On these really close passes where it gets too hot, and the near IR spectrometer, it's radiatively cooled, and if it gets that close to Bennu, the cooler goes bad. So we can't take those near IR spectrometers. We're coming down to 40 meters. The lowest we could do that at was about 500 meters, and that had like a 3 meter spot size. So that's not enough to see details in those rocks. Okay. The thermal spectrometer actually can keep going, but we just got those data, so we'll see. But we don't really expect to be able to make those distinctions.
And is there any chance to check whether these large rocks, the few really big ones, whether they are all on the surface or whether there are some of those also more central? You know, like when you shake a box of cereals and you have the cashew nuts pop up and settle on the surface, or whether they are uniformly distributed?
I know people are working on that. The main way you get at that is actually measuring gravity, right? Looking to see if it's a homogeneous gravity or not. And that turns out that it's the particles. We have these particles that are putting themselves in orbits. So we have test particles that are going around in orbits, and we've actually gotten much better measurements of the gravity field of Bennu based on those. And so people, I don't think we have the answer yet, but people are studying that gravity field to see if we can figure out sort of the internal structure, whether it's homogeneous or there's a couple big rocks. It does look like it doesn't look like it's homogeneous, but I think we don't really have the answer yet.
And very last question from my side. When you use the nitrogen to blow up particles, is it actually strong enough to go like a few centimeters?
Oh, yes. We've done tests, and The reason we need to go have a backup site is because we're pretty sure that if we go to the primary site and fire the gas bottle, it's going to basically completely wipe everything out. It's going to throw rocks meters, and we're doing navigation on those rocks. And so if we move them, we'll have to go re-measure all of the rocks we're using to navigate with. So we expect to be throwing large rocks, multiple meters with that. It's 10 kilojoules or something, and the escape velocity is 10 centimeters a second. And so we're definitely we're gonna make a mess when we go.
Okay, so you're gonna have also a little bit of a kind of average depth information from the surface.
Yeah.
Perfect. Nice. Thank you.
Okay, so let's go to Jayadev for a question and then we go to the audience.
I'll keep this quick. Thank you very much. That was super exciting. And you might have covered this in the talk itself, but those particles, have you any speculation on how they're emitted? Is some kind of a landslide there, or?
We have several hypotheses. It doesn't look like electrostatics can do it. One thing that could do it, and actually has been seen on the Earth, if you go look on YouTube, there's these videos of spalling rocks, which are basically thermal cycling that cracks the rocks, and you can get them spitting pieces off. And so we're thinking, basically, the thermal cycling can put some stress in a rock, and then pieces might spall off. That's one possibility. It's conceivable you could do something like uncover something, and then maybe dehydration of the minerals would do it. So I think in detail we don't know. It's conceivable that it could be cratering, that maybe micrometeorites come and either knock stuff off, or maybe trigger one of those other mechanisms, right? If you have a rock with a lot of stress in it and you hit it with a micrometeorite, maybe that makes it break into pieces that are then able to fly away. So we have a lot of ideas, and we're having a good time.
Thank you.
Okay, so looking at the Q&A, the most upvoted question is probably one that you get all the time. What are the chances that Bennu is going to collide with the Earth?
Chances Bennu is going to collide with the Earth. It's if it does, I think it's in the year 2180, or thereabouts, and it's like 1 in 5,000 right now. Bennu is one of the 2 most hazardous asteroids in the solar system that we know of. And we know of we pretty much know the ones big enough to do that. And so there is a chance we will improve the orbit. We are improving the orbit. There is I think it's 2130 something. It makes a close pass by the Earth. And at that point, it's really not before then that you can say what's going to happen after that. It's too chaotic. It ends up depending on things like the atmosphere and of the Earth in detail. So it's 1 in a few thousand. It's one of the reasons we wanted to go. It was one of the reasons that the target was selected, is it's potentially hazardous. Let's go find out more about it. Because it's really a rubble pile like this, there's always a question of what would you do if you have enough warning. Of course, actually, it turns out if you have enough warning, if you go paint half of it white, that's enough to push it out of the way. Just make sure you push it in the right direction. So 1 in a few thousand, definitely not nothing, not like something to panic about today, and something to continue monitoring. So people need to keep watching Bennu.
Okay, so the next question from the audience is, what are the questions? So this is from Regis Lauchon. What are the questions that we want to answer with the returned material? Are there specific questions, or is it a case of let's see what we get?
Well, of course we will do let's see what we get, because that's but one of the things that we did just about a month ago is have an exercise where we said we've learned all these things. Everybody go write down what the people analyzing the samples should be looking for. So one of the biggest questions is this something that is this a meteorite like Murchison or Gay or our known meteorite, or is it a wholly new thing? If it's completely different than the ones we've seen, we're going to have to rethink a little bit what we know about the composition of the solar system, right? Our knowledge of the composition of the solar system comes primarily from meteorites. because a couple of meteorite compositions for the things we can measure in the sun match very closely. So we say, okay, that must be the composition. If we're not, if the bulk of the real meteorites, of the asteroids, are really different, we're going to have to think a little bit about the details of that, and that'll affect our ideas of planet formation and some of that stuff. A lot of people have a lot of models about how asteroids form, how planets form, and I think by studying these things and the fact that we have these big rocks that are so low density, that's a thing that's probably important actually for forming rocky planets. That might be something that we need to work out. Anyway, people have come up with a whole list of questions. My subfield has kind of come up with those, and I think other subfields have come up with some other ones.
Okay, that kind of answers the next question I was going to pull out from the audience. That was the question by Conrad Tristram about the formation of Bennu. Okay, let's go to Giuseppe next.
Yeah, thank you, Evelyn. Hi, Michael. Thanks for the talk. I would like to know which are the chances that the particle ejected by Bennu will eventually form a ring, or is it too small for doing that?
They won't. So they don't stay around Bennu long enough. Bennu is a very irregular shape, and so they're not stable in orbit around Bennu for more than about 100 days in the best case. So they won't do that. It's possible they'll make meteors. So they'll go into orbit around the sun along the track of Bennu's orbit. And so we have a student who's looking at the possibility of a meteor shower from these particles ejected, but they're not stable. Bennu is too crooked shaped for something that small to be stable, and mainly because solar radiation forces will push it will tweak the orbit too quickly.
So it's more a matter of the shape than its mass.
It's the shape of Bennu being irregular combined with actually solar radiation.
Okay, thanks.
So there was actually a question in the Q&A about the shape from Jorge Quadra. Did the asteroid get the shape recently, being a near-Earth object, or did it already have that belt feature around the middle, Bill?
Right. So going in, I expected this is definitely a topic of some discussion. Going in, I thought it would be a very young shape. My guess was 50,000 years. That it was just due to the spin up and spin down, and it was a near-Earth thing. Those craters, the biggest craters, are clearly older than that, and they're on the equator. So it's pretty clear that the equator, that equatorial bulge, has been there longer than tens of thousands of years. It's got to be multiple millions at least. It is true that because we learned this from Hayabusa 2, they set off a little bomb, and so they were able to see how big of a crater it made, and it made a much bigger crater than we were expecting. So when we first saw these craters, we thought they were 1 billion years old, but then after Hayabusa 2 did that experiment, it turns out that craters on these low gravity objects are bigger than we expected, and so maybe it's 100 million years kind of timescale, but not near Earth space kind of timescale. It has to be older than that, and that was one of the big discoveries.
Okay. Thomas, you just said you have a question?
Yeah, so I'm fantastic talk. Thank you very much. Like, this was really great. The spacecraft is in orbit around Bennu, right?
Yes, mostly. Actually, right now it's we did match point rehearsal and we flew away, so we're going to come back. But we spend most of our time in orbit, about a kilometer radius.
Yeah. Is the navigation accurate enough that you can say something about the inner structure of Bennu?
So the navigation it can be. We had planned to do an experiment where we actually turned off all of the active control and just watched the spacecraft evolve, and that would have been accurate enough to do it. People were reluctant to do that. It makes them nervous not to be in charge of the spacecraft. But then, as I said, the particles are doing that for us. right? The particles are in orbit around Bennu. In fact, there's lots of them in all different directions. And that's turning out to be better than we would have been able to do. Although, of course, with the spacecraft, we know exactly how we built it, right? So we know the forces, whereas the particles, we have to, our model has a lot more unknowns in it, but there's a lot of particles. So it turns out that we were hoping to get basically fourth order gravity, degree and order 4 spherical harmonics of gravity from the spacecraft. And that was the best we could do. And you'd be able to see if there were any big lumps inside, but apparently we have, I think, we have all the terms to 6th order, and we have some of the basic ones to 8th order based on the particles. So we're actually going to be able to do better than we would have with the spacecraft.
So this double tetrahedron shape that seems to be, you know, universal shape in the solar system that makes these asteroids, is there a model behind it?
So I thought, again, this was going in, so a lot of those shapes that we see, we come from the radar data. I took a lot of those data. And so the hypothesis was basically that it was a spin phenomenon, that basically the solar radiation is spinning up the asteroid, and so as materials moving to the equator, and the details of why it makes that shape specifically is complicated, that we don't really understand. There's another hypothesis that was just published that is saying that it might be a pure formation from a big explosion, that if you blow the material apart, that it does naturally come into that shape. We will continue to study this. One of the things that's happened with the mission is, again, we're really focused on site selection and delivery. It was all to choose the site, all to get there. And only now we're really able to stand back and say, okay, let's go back and study this as scientists for our own sake, as opposed to just to do the site selection. It's been a very interesting experience for scientists who aren't usually having to deliver products on days. Right? It's like, I don't need to know the best answer to that. I need to know the best answer I can get Tuesday at 2 p.m.
Okay, I have one final question, and it's kind of in response to what you were saying, in response to Maren's question. You were saying about how when you try and get the sample, you shoot this jet of nitrogen and rocks go flying. I mean, what's the risk of the sampling arm becoming damaged, or I've forgotten the word, the mission, that the orbiter becoming damaged during that process?
We've looked at that in some detail, as you can imagine. We have specifically put some, so like what we call the sample camera, again, it has those 3 lenses, so that if the first one gets all smashed up, we have 2 more. There are 2 navigation cameras, so that if one of them is damaged, we can use the other one. It does not have a cover. We think that the odds of the optics of the spectrometers maybe not being so good afterwards are that could happen. We don't think the odds of it actually damaging the spacecraft are all that high. Partially, we're pushing the gas in and it'll kind of spread out. We think it'll kind of come out like that. There's been a lot of simulations, a lot of testing in the lab, and we don't think it's likely to hit anything too serious. There could be some impacts on the solar panels. One could imagine loss of efficiency, but we don't think it'll break them. And so, but we also know that we can't get the sample unless we try. So it is one of the things where there is some risk. We think it's not all that high. We were expecting sand, so most of the tests have been done into much smaller bits. On the other hand, you're not going to launch the bigger particles. If we do push a meter-sized bowler aside, it's not going to be moving meters a second, right? Because there's an amount of energy, there's an amount of momentum that we can transfer, and it looks like it's okay, but we do also have to go try and do it. So there's always some risk.
Yeah, well, fingers crossed.
You said that you can come back and sample 2 more times.
We can, yes, we can come back and sample 2 more times. Again, if we just didn't get enough sample, we would probably go to the backup site, because again, blowing the bottle scatters all the rocks, and so we won't be able to and we're using them to navigate. right? We have a model of the surface, and we're comparing the images to the model and saying, here we are, here we are, here we are. We move all the rocks, we'll have to go measure them again using this camera that might just have gotten scratched. So we'll probably go to the backup site. If we have to do it a third time, we'll just have to see what happens.
Okay, Maren has the final question.
Yeah, since you just said if you don't get enough debris from your first attempt, you can go to a second location, to your backup location. Is there a chance in your sample container to separate?
No. No, it's one container, and it would all, whatever's in there will get mixed. Okay. That's just, yeah, no, there's only one. We won't worry.
No,
if the sample comes home, we're going to be happy no matter what it is. So
I just want to say it's already exciting enough. So
yes, I mean, I don't know if you know, but the Hayabusa mission that was originally, they thought they got nothing. It turns out they got a few milligrams of sample of thousands of crystals. And I went to one of their first science team meetings where they had all these analyses of these tiny little things. It's like they didn't get what they wanted, but it was the first sample of an asteroid that was taken, and they got a lot. So even if we don't quite get what we want, and I'm pretty confident we're going to get it, it really looks like we've got it mostly solved, then we'll still be happy with what we get, I'm pretty sure.
Thanks.
All right, so thank you all very much, and especially thanks to Mike for this wonderful talk and for telling us about your work. That was really beautiful overview and summary and outlook. We're all looking forward to the, is it going to be a ballistic return? I think it's a ballistic return, right? It doesn't have landing the capsule.
On the Earth?
Yeah. Yeah,
so on the Earth, it's, there's that white capsule, and it gets shot off, the usual aerobraking, and then there's a parachute. It lands at one of the military test ranges. It's almost exactly like the Stardust mission.
Okay, so it just comes down full, well, parachute speed. Right?
It has parachutes at the end, so it doesn't hit at 11 kilometers a second.
Would not be advisable. I need to be out of the sample. Okay, so all the best of luck for that, and
thank you.
And hopefully we will get the maximum amount of mass in the sampler.
Yes, we're all looking forward to the kilogram.
And more. All right, so let's wrap this up. Thank you so much, everyone. Thank you to the panelists for being around and asking fantastic questions, and thank you to the audience for sticking around. And all of the talks, of course, will be on the Astrofísica YouTube channel. And also this talk, we will be putting it on the English and Spanish soundtrack with higher quality, of course. Our next scheduled talk in this series will be on August 27th. It's going to be given by Chris Lintott, who will be telling us about surprises in big data, adventures in the Zooniverse. Okay, so there is nothing left to say except to thank you all again. And thank you, Mike, and see you all around, hopefully very soon on this channel. Stay safe, stay healthy, and until next time.